Hello from Stuttgart. It's Wednesday, the 23rd, and today we talk about percolation.
Minute Material Innovation Nanotechnology Talk. Yip, 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 yip.
Okay, last week we talked about EcoTouch 1, which was a P.PSS carbon nanotube composite for TCF, and I showed you why the environmental stability was better, because of the reinforcement of the CT. Today we will have another topic. We will compare rod-like conductive fillers against flake-like conductive fillers. But before we do this, please check the GDD. So the temperature fall, it's a bit chilly today and very windy, but the sun is shining. I gained another follower, so I'm still trying to catch up. And of course, Mr. Bill Gates is still increasing his numbers of followers, which means that the race is still open. But I will probably beat him by end of this year. I don't know. I do my best, as you know. Maybe you can recall last week I showed you the benchmark, the figure of merit of ITO in terms of transmission and conductivity, and how we try to beat this figure of merit with carbon nanotube composite in different way. And I think it's very, very important to understand what's different between ITO and carbon nanotube, because it's the structure of the particles. So you can basically set up your TCF, your transparent conductive film, with a crystalline or network type of conductive material in the crystalline type of material. So you have no big particle heterogenic issues, right? So whilst in the rod-like type of transparent conductive material, which is carbon nanotube, you of course have this to face this challenge to making a good network. So to understand with a simple demonstration how to make a conductive network, you can simply imagine this screwdriver is a nanotube, which has a probably in the best case, it had a ballistic conductivity, which is super duper conductive, and it's very thin, and it's probably not so long. And you like to making a big area full of this nanotubes because you like to have the whole screen conductive. So this means you need another nanotube, okay? And then you have these contact points. And then you have not only one contact point, you got billions of contact points. And in this case, the conductivity is transmitted between the point of contact of the nanotubes, okay? So this is the principle. You build a network and the current is flowing through the contact points of the nanotubes, in this case of the screwdriver. And the more nanotube you have, the more conductive it will be. But of course, the less transparent it will be. And this is one thing which is probably the holy grail holy grail of working with nanotube is how to disperse nanotube in that way that you got a good percolated network and maintain the good conductivity. And then of course if you use surfactant and other things to make the dispersibility a bit better, then you have impurities between the connection points, in this case again the screwdrivers, which then can lead to lower conductivity again. And as a result, many people are looking for a conductive binder. But now you think, okay, nanocarbon, I understood carbon nanotube, which is like a screwdriver. What about graphene? I will show you now. First of all, we are not looking for a conductive binder, for a conductive surfactant, but let's go back to graphene. And the thing of graphene is what is really interesting is that every layer or one layer of graphene is absorbing 2.3% of light. And this is very, very interesting. So why it's interesting? Because if you have a transmission of 95%, you can say, I got two layers of graphene. Isn't it beauty? Theoretically. In reality, it's a bit more complex. But what we learned today? We learned today that in rod-like type of additives or conductive fillers, you have to build up a percolated network. Think about, again, the screwdrivers, thousands of screwdrivers, which like to making a network which is conductive to transmit current through the area. And you like this to have to use as less as possible of these rods, because not only because of cost, because to having a good transmission. And the key problem is how to ensure the conductivity on the contact point between each nanotube, and this 1,000 times. And to do this, you have to find a good way to disperse nanotube in a way without using surfactants and other materials which are harming the nanotube or making impurities which are not conductive. This is what we do at Fraunhofer IPA, what is a good thing. And the other thing what we learned today is that graphene is another option to make in transparent conductive film, and one layer of graphene is approximately absorbing 2.3% of light, which makes us very easy to measure the thickness of a graphene layer theoretically. That's it for today. I wish you a great week. Stay healthy and see you next week. Bye bye.
MINT, Material Innovation Nanotechnology Talk. Yip, 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 yip.